Yes, thank you. Hi. I think it's a good talk before lunch. I'm going to be talking about short proteins. Okay, unclonable polymers and their cryptographic application. This is joint work with a bunch of people. Here is a legend. So Rada Al-Mashakbe, Ran Canetti, who was here before, is here. Yeah, myself and Eran Tromer are cryptographers, who hopefully you all know and love. Yaniv Ehrlich and Itzik Pe'er are computational biologists, and Johnny Gershoni and Anna Reutberg-Berman are biochemists, wet lab people. They're the ones we managed to find who were brave enough to talk to us. Good. So let me start with the preview. Please, no questions during the preview. It's short. It's meant to bring questions, but I don't want to answer them. As soon as the preview is over, you can ask questions. I encourage it. Okay, so this is like a big summary of what I'll talk about. So we propose a new biological approach, which includes both a biological process for the honest parties and a biological hardness assumptions against dishonest parties. I want to note that the good guys, the honest party part is also really, really hard. It's not just, oh, let's talk about the hardness. And then we use this new proposed approach to construct something we called consumable tokens, which is a extremely very weak version of bounded query memory, something like one-time memory of GKR, Goldwasser, Rothblum, and Kalai, who happen to be here, yeah. And then we use that to construct some cryptographic applications, which are digital locker and some version of K-time program. So I'll explain what all of this means. So if you start from the consumable token, you can just think of it as a very simple primitive. You can forget all the biology. What can you do with this very weak primitive? Okay, but actually modeling it and coming up with the primitive, a lot of the work went into defining the right primitive that we could justify in biology. And then some kind of formal way to say this is justified by biology. So there was a lot of work there. Okay, good. So I'm gonna, let me say what the critics are saying. I'm not gonna read it all. Can you see it well? You can read for yourself. Can anybody guess who the next quote will be by?
Ron?
Correct. The Ran Kennedy quote is made up, but everything else is in fact true. There's a tiny asterisk. It was in fact said, but not about our work, just in general yesterday on the panel. Yes, I could be a journalist, right? But anyway, I feel it's appropriate, so I quoted it. Okay, good. So that's the preview. So I'm gonna keep it low on the technical details, both because of time and because it's not clear to me what to focus on, the biology or the crypto. The biology I don't know about, but the crypto is like more standard, and although there's some non-standard things in the crypto that come because of the biology. So I'll kind of try to do everything, but at a high informal level. If you ask a lot of questions and I don't get to something, that's fine too. Yuval, you'll tell me about this is the same slide as before. You'll tell me about time, how much time is left, etc. I forgot to know this. Okay. All right, so let me start with very informal, high level. Assume you had a bounded query memory device. Okay, what does it mean? There's a memory device, it has some message M in it, and you want to be able to retrieve it, but then as soon as you retrieve it, it self-destructs. Okay, so it's a one-time, you can read it and that's it, then it self-destructs. Obviously, it has to be unclonable, otherwise it makes no sense. You clone many times and then you can read it many times. Okay, that's a bounded query memory device. It's something useful that we would like to have. By the way, a lot of the slides are made by Rada Al-Mashakbe, just to give credit, including whatever you're trying to read there. This message will self-destruct in 5 seconds. Okay, You can also think of a slightly more general idea of a memory that doesn't have just M, but has like 4 messages, MYXA, and you're allowed to retrieve any 2 of them. But as soon as you retrieve the 2 of them, they self-destruct. Okay, this is a primitive that's really useful. I'll call it bounded query memory device. And it was shown to imply bounded execution software, like a one-time program. Like you can have a program, arbitrary generic program that anybody could use a certain number of times and no more for a limited time. Okay, so this was given by Goldwasser, Kalai, and Rothblum. I'll say a tiny bit more about it in a second. In the classical model, it was also done in the quantum model by Broadbent, Gutowski, and Stabila. Good, but how did they get? I don't want to focus on this transformation, but more on how the bounded query memory device, where did it come from? How do we build it? Okay, so in the GKR, it was just a hypothetical device. It was a very small conceptually thing. It's just a 1 out of 2 of T. There are 2 messages, you take one and then it self-destruct. Okay, and using that, they did arbitrary program, limited time execution. But where do you get it from? So the only thing to do it from, or I guess there are many related works that I could talk about and I won't, but the point is, oh, we could just use hardware assumption, tamper-proofing it. But I want to point out that as far as we know, there is no, the fact that it's such a simple, small, nice thing is not so helpful in hardware. There's no, like, in order to have tamper-proof, you just need to assume you just tamper-proof the whole process. You might as well just tamper-proof everything. It's an assumption that's not, we don't know how to achieve it from smaller components. And also, you know, there are side channel attacks. Does this assumption really make sense? Also want to say, I didn't think about this deeply, but it seems to me this assumption is also, the hardware assumption is not a win-win situation. If it turns out to be false, then it's only a lose. But anyway, this hardware assumption is something sort of competing with ours, but we suggest a new way to do it from biology. Okay. So this is what we want to do. So our points are unclonable and self-destructive memory devices. Okay, I sort of said that. There's formal modeling and analysis, and what we get is really, really weak. And so we need to do amplification. And for amplification, we use both standard crypto stuff and also less standard because there are things that are annoying that need to be dealt with. Okay, and then we show some cryptographic applications. Hopefully there'll be more. Okay, so let me give a taste of how we build it from biology. So let me start with something that we do not do. This is not us, but just to motivate. DNA is something that's really robust and amazing. You can find DNA from 1,000 years ago, dried up, and easily make 1 million copies of it and sequence it and reading it. It's great.
Not so easy. We got a Nobel Prize for that.
Okay, but their work can now be used, right? This was a direct quote from a biologist, what I said about the 1,000 years ago, dried up 1 million. I did, yeah. But, you know, anyway, not the one who got a Nobel Prize.
We don't lie in introductions.
Anyway, this is not what we do. Okay, so what is a DNA? It's like, what's the, and then there's recently, or maybe it's not so recently anymore, there are work that suggest to use DNA for storage. So you have a message, you encode it into a DNA. This is not hard, it's robust, it saves, keeps for a long time, it's great. However, it's the opposite of what we want we wanted something to be unclonable, okay, not so robust. In fact, we want the opposite. So we wanted to do something biological, but the main thing that people do, DNA-based, is not appropriate for us. In fact, it's the opposite, okay? However, there's a different type of polymer, which is proteins. In fact, okay, proteins is what we do. Proteins, I'm told proteins refers usually to a very long sequence. And for us, it's a short sequence. It's called a peptide. But in any case, this is a different type of a way to encode a message into a sequence of things. In this case, it would be amino acids. And it's also not so hard, maybe a little harder than DNA, but it's not so hard apparently to build. any short sequence you give me. I could build, going through a DNA, I could build a peptide, a protein that encodes it in a sequence. Okay, but it is not clonable. And it's not easy. We want to say it's not easy to read it back. Okay, so why do we want to say that? So this is the central dogma of molecular biology. This is a copy of what Crick wrote in 1957. This is something biologists know. It's famous. Central dogma, this is his words. The central dogma is his words, but the lines are ours. Once information has got into a protein, it can't get out again. Information here means the sequence of the amino acid residues or other sequence related to it. That is, we may be able to have, you see, DNA to RNA, RNA to protein, DNA to protein, DNA to itself, which is like cloning, RNA to itself, RNA to DNA. We can do all of that, but we can never go from protein to DNA or protein to itself.
Question. So your goal is to try to do a one-time program using biology, right?
Yes.
So you want to encode the information instead of using hardware, using biology.
Yes.
It's not, the main thing there is the self-destruction, right? That you can read and self-destruct. It's not like, it seems like what you're saying here, oh, it's like self-destructive by definition because you can't read.
Oh, wait.
I don't understand your question. It's self-destructed not just because you can't read. I'll say a little more about it, but I don't understand your question. Tell me again.
Okay, so what you're trying to do, I mean, what you're saying is, oh, it's great. I'm going to use encode my thing in a protein.
Yes.
Okay, but I need to then read it.
Yes. Oh, so you're saying, how do I read it?
You just say you can't read.
Good. Yes, I agree. Okay, this is just the starting point. This is why we needed to work hard to make it happen. Yeah, but now I understand your question. Yes, good. I'll answer.
So, but was Crick talking about like what humans can do or what the body does?
Okay.
Like a protein is there, I can look at it in a microscope and I can read it, right? So
Good, good. This is related to, you want to say something? This is related to your else question. You guy said if a protein is there, I can look at it and read it. You can't really, you cannot read it. I'll say a little more about it, like in one more slide. Ask me again, both of you. I just wanted to, so I mean, what he talks about is both like the human body and technology. Okay, that's what he thought. That you can take a protein. So if you give me a DNA, I can build a protein out of it. Given a protein, I cannot build a DNA out of it, and I cannot make another protein out of it. About reading in a microscope and your else question, I'll answer in a second. I just want to say this picture that he drew looks exactly like the pictures I draw in my crypto classes, right? It's really the same. That's basically what he's saying. So we want to take advantage of it and do some crypto out of it. So good. Now let's talk about the reading. What is reading? Which microscope? So the microscope you mentioned is called a mass spec, mass spectrometry device.
mine was a theoretical microscope.
So in fact, it is possible to read proteins, but what is read? Read is sequence. What is the sequence that composes them? It's extremely hard. You need a lot of material and it needs to be very pure. Okay, this is what our biologists, co-authors tell us. We kept asking them and pushing them about, well, but maybe it's easy, maybe the adversary could do it, maybe the adversary has a stronger mass spec. Just want to say all our culture of discussing with them, with the biologists, it's obvious to them that an adversary cannot do it, but they're a little worried about our scheme that the good guys might not be able to do it either, because reading is really hard. Okay, so this is the point, but we hope it looks really good.
Now, when you say you need a lot of material that needs to be pure, you mean the proteins or the chemicals?
The proteins,
So you need many copies of it?
No, not many copies. Okay, so you need a vial with some stuff in it. The stuff needs to be pure, and you put it in the machine, this machine, and the machine reads it by breaking it up into little pieces, and I don't know what measuring, I don't know what it does, and tries to read it, and something comes out. At that time, this was destroyed. So you need high purity in order for the reading to be successful, and you need a lot in the sense that when it destroys the material. Ran, if I am misspeaking, please, I'm not. Or anyone else actually who knows biology, please, I won't be offended.
I think the important there is that they need a macroscopic amount of material in order to read from it. And then it's destroyed.
Oh, it's funny, macroscopic, so yeah, not microscopic, but macroscopic. You need a lot and it needs to be pure.
Copies of it?
Yes, you need a lot in your vial.
Copies of the protein, and it needs to be without other junk inside.
Yes, in order to successfully read.
Yes, and my understanding, I had some friends who did bio, my understanding is when you do the reading, you're shooting it with a laser. And like that's.
Yeah, it dies. So the self-destruct is really completely, it's like burning it. Yeah.
For sure, you can like detect like whether you have two distinct proteins because like that's how we work. So
You can detect whether what?
you have two distinct proteins, so you can like definitely distinguish some stuff because that's
Good. Yes, there are some proteins that are easily distinguishable from each other. I agree. Based on like weight, there are things you can do like measure the weight or the mass or things like that.
and different proteins for different functions, so that wouldn't actually work if they
You have different proteins. What?
for different functions we get different proteins, so they would be all the same. But it doesn't work.
Good.
Which are not.
So for us, they're short. They're like about 20 amino acids. It's not a full protein. It's a peptide. It's short, so it's harder. But indeed, the scheme uses like we don't have all possible amino acids, but only ones that look similar and cannot be distinguished. Things like that. There's a lot of chemical work going into it. Good. But anyway, so what do we do with this? We want to build a consumable memory token. So here is an idea of how to do it. So first you synthesize peptide from a message. You encode it as amino acids and you make a protein out of it. Then you attach a header to it. Okay, but by the way, the biological stuff, which I don't know much about, some of the stuff we're doing is standard bio stuff that all the biologists say it's standard and easy, and some of it is novel biological techniques. Okay, I was told that figuring out how to attach the header in a good way so that it's easy to cleave is a new novel contribution of our work. Great. I don't know. Anyway, right? Whereas synthesizing M into a protein is not as easy, apparently. Anyway, we did this. We being the authors.
There was a lab. You guys actually.
Yeah, I'll show a picture of us doing it in a minute. Good. So you synthesize it, you attach a header. Okay, so a header is also a sequence, a shorter sequence of amino acids. And the header is such that there is an antibody that corresponds to it, right? Which you can send to someone. You can send even digitally the sequence that makes the header that tells you what the sequence for the antibody is that can attach to it. Why do we want to do that? Oh yeah, this is a picture of it. This is Anna, she's a co-author, and this is the vial. So this is really actually this. It's not a stock picture, it's actually Anna. Okay, see, so we're doing it here. And then we mix with decoy proteins because of the purity aspect. You are right that you need to be careful that the decoy proteins are harder to distinguish. Okay, I will say more about it. Sometimes even if you can distinguish and you know the key, still our schemes will be secure. I'll say what I mean in a minute. But anyway, in the most basic consumable token, this is what we do. We mix with decoy proteins. And then the point is that, one second, then the point is this. So this is how do you prepare this consumable token? How do you use it? How do you consume it? So the good guy first purifies by the antibody is the secret key. Okay, the good guy can purify by pulling down the correct protein, and now it's pure enough, or many of them, a macroscopic amount of them. Then it's pure enough that you can run it through the mass spec and sequence it, and then it's gone. The adversary, on the other hand, could maybe try, but every pull down, even with the wrong key, destroys the solution. Running it destroyed the solution. So if you don't know the key, you can't do it. All this is very simplistic.
Explain again what the antibody does.
Yeah, the antibody pulls down this particular header. The antibody is related to the header. So this is before going to the mass spec. There's a pull down procedure. I don't know what it looks like chemically. Nothing. It just takes only the good guy because
Only
it
the
attracts.
ones with the appropriate header.
Yeah, it gets all the guys with the right header that matches to it and pulls all of them down. And now you have a pure solution. And then you can put the pure solution in the mass spec. Yeah.
I'm trying to understand what your token does. Is it like there's two messages in it and you?
Oh, good. I'll give a cryptographic definition in a minute, also not formally. I'll give it in a minute and you'll
But
see
it's
what
not
it
like a
does.
one-time program exactly in the sense that.
No, it's not.
That one, it's something else.
Right. I'll say what it does and then I'll say how we use it.
Okay.
In the end, it will be a one-time program.
It's not will be.
These
We
are
use it in order to achieve a one-time program, but it's not fair to say in the end. We use it plus IO plus one-way function and we get a one-time program, sort of.
There's the first one in the beginning, right? IO is for free.
Yes.
Like a really fast question, like
Sure.
a simple attack, like in my mind, it's like something like you can always, you need like a Markov, like a kind of like amounts of this protein, you can always like break them into two, right? Like
Good.
so then I can like simply take copies, like if
Good. So the adversary can always like just take half of the.
yeah, I just meant like just take half,
Good.
but just
So-
take half of this to the machine.
Excellent. This is a good attack. So ideally, we would want to give the minimal possible that you can read. This is not a good notion because maybe the adversary has a better, stronger mass spec than you. And can't do that. And so what we will do, you will see in a minute, is we will assume the adversary has more power, but still, the adversary can read some more than you. Let me get to it in 1 second. It is a good attack. I mean, I give you little, so you cannot divide it too many times. But you're right that we can't be so exact because the adversary may be richer with a newer, better mass spec, newer technology or something like that. So we will account for this in our model. Good. Here, this is the answer both to you and to you.
It's a fine-grained biological cryptography.
Fine-grained biological cryptography, it's true, but then we use it to build real cryptography that's not fine-grained, which is part of the reason it's hard. Good. Sorry, I don't mean to complain. Okay, so here is now you can forget the biology. Here is something I could define. This is not a formal definition, but we do have a formal definition in the paper. This is a consumable token. Well, I guess, let me think, maybe I should just show, this one is better. Yeah, let me just do this one. Okay, good. Here is our model. This is a consumable token, and it will account for your attack and it will account for your question. So it's a 1NV consumable token. This is a definition you could just define and now forget the biology and do whatever you want with it and see what you can get. So there is a vial. It has V pairs of key message pairs, V key message pairs. Okay. Now it's a vial or an ideal functionality. When you if you submit a K prime that equals one of the rows, you get back MI. Where if you submit a wrong K, you get nothing. Okay, that's sort of the functionality. The good guy is allowed one query and then it's gone. We assume the good guy can never do more because we gave them too little, it's self-destruct. For the adversary, we allow N queries exactly in order to account for these attacks. If the adversary can divide it, more sophisticated. Okay, so we allow so for the security, the adversary is assumed to have N. N is some small or some constant. In fact, everything there is small and constant. It's not big, huge cryptographic length. So we assume this token can be effectively read by the good guy once and can be effectively read by the bad guy no more than N times. Okay, and notice here, even if you do know the keys, all the keys, there's no secret. Even if you know all the keys, you still cannot read more than N things just because of the self-destruct probability.
No way to learn some global partial information, like the parity of everything.
Yeah, good. So there isn't, I guess. So
You're defining an ideal functionality.
Exactly. So there are two ways to understand your question. One is what my definition says. My definition says there is no way. That's the only thing you can do, and that's it. It's an ideal functionality. For the biology, we try to work hard to prove it in under some model. Yeah. Good, you don't get partial information either. I mean, really, in reality, in biology, you could submit some key that is very similar, and maybe it pulls down, and also there's a soundness error that is non-negligible, like you might somehow retrieve something even without a key. So we took all these things into account. Good, so this is the biological primitive consumable token. Okay, good, I think I said these things.
One question,
Yeah,
at theory
please.
level, even if you could get some global leakage, it does not necessarily mean that your construction is broken, or just didn't look into it. So it's possibly more robust even with global leakage.
Yeah, I'm trying to think, maybe we did look into it, we didn't, right? But you're right, it's not,
Maybe you could have an ideal functionality where the sum is you bound the number of bits the actually can learn and you can build something.
yeah, but the thing is, we were, yeah,
No, I think what we were talking about, kind of jumping ahead, but the modeling we're trying to do, we're trying to say let's do kind of little amplification, kind of quote unquote, right? We have this single primitive, which talks about fixed number of bits, and it has some error here, got some error, leakage and the coding error when you want
versus leakage
to purify, amplify, whatever.
yeah, but the thing is, we have much less freedom because we want to be true to the biological thing, so we can't just define it in any way, but maybe it's interesting, and yeah, defining general lambda leakage, yeah. Yeah,
Some sort of answer for how long you can store these tokens, just concretely.
I do not, do you know?
I remember that we talked about it, and they thought that it should be able to keep for a while.
I don't even know, like, is it in the fridge? How do you store it?
The right temperature.
Together with your quantum computer.
Can you give some rough numbers like what NLG look like?
Yes, good, I can. Good, so let me think, how many things? I can tell you some numbers about the length, which is not what you're asking, but the lengths are about like total like 30 amino acids. The key is like 10 amino acids. The amino acid is like 5 bits. That's the length. It's not an answer for how many do we store. I don't know what makes sense. Maybe any number.
These are like
I do not know.
so any number should make sense.
I don't know if there's a real limitation on V. What there is a real limitation of the 1 and N shouldn't be the same. Otherwise, it kind of doesn't make sense and should be bigger.
The keys are constant size or something, right? Because
Yes, the keys are
because the honest
constant
party
size.
also has to
They're about
guess.
50 bits or something like
the
that.
honest party also has to guess corresponding percentage.
Yeah, but it's not a guess. We can give it to them. Actually, by the way,
I was thinking of the future application, right, where
I mean, in my final application, I want normal crypto with long keys. You use the word guess. I also want to say, even if you know all the keys, the self-destruct property holds. It's not a matter of secrecy. It's that in order to get from this weird, dirty biological stuff a message M, you need to destroy some of it. And so you can do it at most n times. Good. Okay, we have an ideal functionality. Let me think about it. Oh, okay, this is a whole thing that I don't want to discuss. But how do we justify this ideal functionality fits the biology? We actually have an even lower level abstraction we call the vector model. The vector is amounts, quantities of each type of, each kind of protein. And then we model how you do, I don't know, pull down or like different biological operations. And then we show that with this more close, we have an intermediate model that's closer to biology, but still math. And using that, we prove that this is realized. But this I don't want to talk about. Anyway, at this point, we have an ideal functionality, FCT, consumable token, 1NV. And the question is what we can do with it. And this is why I said it's really, really, and this ideal functionality has, unlike what you're used to, negligible soundness error. That's important. Okay. It's written in full formality in our paper. Okay. Good. And now we want to like Ran was saying before, we want to amplify it, okay, to something better. Okay, this is highlights of the model so far, not of the future results. The non-negligible soundness is the main thing I wanted to say. And then I think I said everything else before. Yeah, the only meaningful, everything else I said in answers to questions before. Okay, so, and this also I said, the hard part is amplifying weak constant size properties to like standard cryptographic functionalities. Good. So let me say, Yuval, how much time do I have? Yeah, I can finish in any amount of time. I can finish now, I can finish in 5 hours, whatever you tell me. Seriously, it's easy to talk a little or a lot. Okay, good. So let me say something about the applications. I already said about the one-time program, I hinted about it, but that will be my second application. Let me start with the first application, which is digital locker. So you encode a message M with a password, and the point is the password has low entropy, like a password that's easy to run an exhaustive search on. But I want the lock to, after a few, it's like when you enter the wrong thing some number of times, a small number of times, it self-destructs and it locks forever. You can never get back again, right? Because the password has low entropy, so you have to do it. So this is what we want to implement. And this seems like obviously, of course, we can implement it using our consumable token assumption. Oh, this is a definition of the same thing. Sorry, more formal definition. This description, informal description, is the same as point function obfuscation, right? But with bounded query. So think of the following functionality. I have the input is P prime. If P prime equals P, then I give you M back. P is the password, and otherwise I give you nothing back. I'm just writing the same functionality as before in more mathematical terms and pointing out that it's the same as point function obfuscation, with the point being you cannot call it more than a small number of times. It's bounded query. Okay, so there's a password and you query it and you get the message inside if the password is correct, and otherwise you get nothing, and after a small number of applications, it self-destructs. Okay. Good. So the honest party can, it sounds very similar to what we already have. It sounds like trivial to achieve it, right? Because the honest party will just run it with the correct P, and the adversary can try up to N passwords, but it doesn't know P, so it's exactly what we wanted. Right? So just like a spoiler, the answer will be no, not so immediate, but at the end we will achieve it. Good. So the first attempt that seems immediate is you just encode, you just put one message in there. And if you give the K as the password, or, you derive a key from the password, if you put the K, you get M. And if you put a wrong K, you don't get M. And that's exactly it. The problem with just applying it as is without any thought is exactly the non-negligible soundness. Basically, if it had negligible soundness, it would be immediate. By the way, there's also an issue of non-negligible completeness, but I'm ignoring it because this we solve in biological ways by sending many vials. So I'm ignoring it. Whereas the soundness we address in a cryptographic way, so I'm talking about it. Anyway, just using as is not good because there's non-negligible soundness error. So not error, but like the adversary might read it even without the correct key. And so what we want to do, so the next idea is to just use standard amplification technique of secret sharing. So instead of encoding one thing, I give you different vials, and you need to figure all of them out in order to get the message, because it's a secret sharing, and N out of N secret, U out of U secret sharing. Okay, and that does boost the error, the gamma. It boosts it to negligible because gamma goes to gamma to the U. If you just happen to be lucky with probability gamma, you will be lucky on all of them with negligible probability. But that's the standard stuff we know, and that's great. But the problem is there's a different source. You don't have to read carefully. I'll tell you where the source is. There's a different source of non-negligible probability. Now, the issue is, if you were lucky in the first one, just by chance, gamma probability, non-negligible. From this, since the password was low entropy, you can on the side try all possible passwords and see which password mapped to K1 and then figure out all the other K2 and succeed. So because the password had low entropy, even one success, actually giving you many vials, boosts your probability of success, because any one success will allow you to offline attack a dictionary attack and figure out and then read the rest. And so what would, like after these,
it's the same because it's the same K?
Because it's the same, not KP. So the Ks are different, but they're all derived from the same password.
Because it's the same password.
Yeah, and the whole point was that it's a low entropy password. Yeah, good. So after you know all of these problems, finding these, somehow we looked for applications that seemed obvious and then they were not obvious. But once you know all these problems, solving it is actually not so hard. So what we do, I don't want to go into the details, especially since I promised Yuval I can finish at any time. We do secret sharing, but we make sure that even if you're lucky in one of them, you need to be lucky in all previous ones in order to read it. Like we have high entropy secret encoded that chains into the next vials. It doesn't matter if you don't see it now. It's not hard, but it's interesting to figure out that this was an issue. Okay, so anyway, we succeed to do BPO, bounded query point function obfuscation. That was one application. Okay, and it works. These numbers are not exact, but pretty good. So this is negligible error probability in addition to just n trials over the password space, which is small. Okay, so now I want to talk a little bit about the application about achieving 1n time programs. I'll tell you what this means, 1n time programs. So that's the next application that we want to achieve, and that's the one I hinted about from the beginning. So just good. Let me say what 1n time programs are. First of all, one-time program. What's a one-time program? It's a program that you can run once and then it dies and you can never run again. Okay. In my terminology, this would be called 1,1 time program, just so you know. But I have 1,n time program. Why? Because I need to distinguish between the good guy and the adversary. So it's a program that the good guy can run once, and then I cannot assume it can run it anymore. Just once and it dies. But the adversary can run it n times, and then it dies. Okay, so I have a gap. So I don't exactly achieve the one-time program or the k-time program. I achieve it with a gap from my consumable tokens. Okay, so this is why I said we achieve a version of, so we don't achieve k-time programs, but we achieve k plus 7 times program. So the adversary can run it more times than, just because we assume the underlying consumable token has this property. Okay, so this is what a 1n time program is. Okay? Clear?
Do you have a mathematical definition of the severity of that?
Good, I do, but not here. Let me see if I have, I don't know if I have, not here. I have in the paper. The paper is on ePrint, and I can talk about it. The mathematical definition is, it's an idealized functionality. Everything is in the UC model. So the ideal functionality can, I can tell you more details about it afterwards.
This is sort of like a ramp setting.
It's like there's a ideal functionality. You can ask it to generate a program. It generates it. Then if the adversary asks to run it, there's a counter, and after you run it n times an arbitrary inputs of its desire, it distracts. It will never answer again. Yeah.
Is there a barrier to building one-time programs and one-command time programs?
My intuitive answer is yes, but I asked this of my co-authors and they're all like, yes, of course you can't, because the adversary maybe has a stronger machine. And I asked, well, but do we have like a real impossibility result? So I don't want to say confidently no, but I don't know how to do it. if you want to allow the adversary more. If your consumable token is your primitive that has a gap between the 1 and the n, I don't know how to achieve KK time program. I don't know if maybe it's possible. I think I don't want to misrepresent my co-authors, but I think they're more confident than me that it's impossible. Okay. Good. Yuval, has it been 10 minutes or no?
Getting there.
Getting there. Okay, so let me just say, there's a one idea, let me say it as follows. Like before, there's one idea that's I forgot to say also importantly, when we talked about assumptions before in the panel, one thing I really agreed with is we need to specify our assumption, not just say, oh, now we do it. So in addition to the biological assumption that I talk so much here, we also use one-way function and IO to achieve it from consumable tokens. Good, so the main idea is this, and then there are complications because things are short, and so we do some error correcting code and blah, 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 and we make it happen. That's the big point. So let me say the simple idea before adding all the complicated, not so complicated actually, like error correcting code and things like that. The idea is this. I have a program, F arbitrary program. I want to be able to run it one time for the good guy and n times for the bad guy, at most n times. So for each input in the input domain, I have a secret message stored in the token. And then I obfuscate a program that does the following. You know, given the secret message M that corresponds to X, if M corresponds to X, I obfuscate the following program. I give you X and I give you M. If M and X fit according to this secret mapping, then I output the correct output F of X, otherwise I output nothing. The idea is in order to be able to run F on X, I have to use the token to get the secret message M, and then I can use the obfuscated program and get what I wanted. But now I destroyed my token and I cannot run it again. That's the main idea. It doesn't really work because the token has only short messages, only a small n number of messages. I want general programs on, 0, 1 to the n. I want many possible inputs. There are issues, but those issues can be solved just in order to F with large. So this sort of works, maybe even this not quite work. But it sort of works if F had very small domain. If F has large domain, it doesn't work, but we make it work. So we have an error correcting code, but then we also need to account for the fact that when you have many vials with many things, you don't want, that gives more chances to the adversary to get this non-negligible advantage. So you want to set up the code parameter so that it doesn't help him. But anyway, we succeed to do that. So, yeah, that's the end of my talk. I think it's exactly according to the time Yuval gave me, right? Yeah, let me say something about future work. Yeah, even the current work, the biology, let me just say something about what we did already biologically. We have an implementation of the token. We don't, of the token, and it was really complicated for the good guys. I'm talking about the good guys. It was really complicated to do it, but we did it. We haven't yet read it in the mass spec, and they think it's possible, but there are funding issues. And there was a big delay due to they were working on COVID vaccines. Seriously. But there are challenges, not just funding, also intellectual challenges to do it. But I think at this point, I'll let you say in a minute, I think at this point, we were planning anyway to write a biology paper with everything they did, even without the missing parts that they didn't do. They thought it's interesting enough for a biology paper. That's in biology. And in cryptography, there's a lot more, many more applications you can think of, talk about it, etc. I'll take questions, but Ran, yeah.
COVID is not just a lame excuse, but actually all those labs, all those techniques that we're doing actually were all harnessed to do COVID vaccines. It's the same techniques apparently. Already if I'm speaking, let me just say something I want to comment later. Is that it really annoyed us, at least me annoyed, that GPR do this one-time programs very nicely with just YAO, one-way functions, and one-time memory. And now we can slightly mess up the memory, and the only thing we can do is a full-fledged YAO. Can you do something in the middle? And we thought about it quite a bit, and we have no way of doing it. And that seems like.
But we don't have a barrier either, right?
Yeah,
We
there's
just
no
don't
barrier.
know.
But,
So-
I mean, there's this paper.
The barriers are stupidity, but whatever. That's a barrier.
So
Can you say something that you didn't say about win-win for the assumption?
About win-win for the assumption. Okay, that's again a
Just make fun
biology
of us
thing.
assumption, of our assumption.
Yeah,
Or
yours-
do it.
yeah, I
Just
see.
say something.
The hardware assumption, yeah. Good, if we could read proteins, easily sequence proteins. My feeling is this was revolutionize the world, but how exactly? Good, so I don't really know. I asked a friend of mine, but I just asked him this morning, seriously. I can find his answer. Let's see if I remember it. What?
Is he also a cryptanalyst?
No, he's a PhD biology student at Columbia, but his like everyday work is related to mass spec. So the first thing he said, I said, what would happen hypothetically if it was easy to read protein and duplicate proteins? And he's like, well, first of all, my life would be in the lab would be much, much easier running lab experiments. I don't have to throw away the protein and start over from DNA. Okay, but this, maybe PhD students should have a hard life. So this is okay. But the other thing he said is, let me try to remember what he said. He said, you could see, oh good, here's something he said. So given, let's say you had a virus and that you don't know anything about, you know, you were infected from this protein, but you don't know how. If you could sequence and read it, you could learn a lot about the virus, the proteome, I think it's called. As like genome, there's proteome. So proteomics? I don't know. Anyway, given so the example he gave is if there's a virus, we could find out if you have the protein but not the DNA that generated it.
you have a non-pure, an impure protein, a protein with lots of other stuff.
I mean, it's always impure usually. It's always impure. I just remembered something I forgot to say. 1 second, let me think. It just. Yes, I remembered something. The mass spec related to the beginning of my talk. Not only do they need it to be pure and a lot, they also, the way they read it, they have a code book with a list of known proteins and they somehow need to look it up. They don't know how to read a protein that's random, that they don't know anything about. It's really, really hard to read protein. So this will help you learn all of this. But somehow I feel like, you know, breaking the central dogma of biochemistry sounds better than side channel attack, no? I don't know. In any case, having many assumptions is good, right? It challenges. I'll put back what the critics say in the first slide.
Yeah, we can continue this fascinating discussion over proteins. And because of your good behavior, you have 93 minutes for lunch. That's 3 minutes. Courageous stuff.